In this video, we are going to investigate the principle of total and effective stress in soil. The principle of effective stress is one of the most important principles to understand in geotechnical engineering. Several engineering problems like determining the bearing capacity and settlements of soil are based on the effective stress level or change in effective stress. Effective stress is also important when evaluating various soil parameters, since both soil stiffness and strength are influenced by the effective stress level. Generally, effective stress in soil is either produced from the overburden pressure of the overlying soil or from a load placed on top of the soil. In this video, we will only be concerned with the stress produced by the pressure from the overlying soil. If we consider a soil volume with a specific area and height, it will exert a force on the underlying soil. The magnitude of the force is based on the unit weight of the soil and the dimensions of the soil volume. The magnitude of the stress caused by the overlying soil is determined according to the general stress definition. Newton's third law states that for every action in nature there should be an equal and opposite reaction. Therefore, the stress induced by the soil volume can be visualized as an equal but upward stress at the bottom of the soil volume. In geotechnical engineering, we prefer to perform the stress calculations as one-dimensional, since this makes knowing the area redundant. If the two expressions shown are combined, we get the one-dimensional stress definition. This expression is also the definition of what we call total stress. Total stress is defined as the total weight of soil and water. This definition of total stress is valid whether the soil is below or above the groundwater table, as long as the water table does not exceed the terrain level. For the soil volume showcased, the total stress increases linearly as the height of the soil layer increases. The stress calculated corresponds to specific points in the soil. If multiple soil layers are considered, the total stress is determined by adding the contribution from each soil layer. The slope of the total stress curve for the new layer depends on the unit weight of the soil. Often we are not directly interested in the total stress. The total stress generally consists of two components, the effective stress and the pore water pressure. If we take a closer look at the soil particles inside a coarse-grained soil, there will be two stress components of the total stress. The first component is the effective stress, which arises from the contact forces between the soil particles. The weight of the soil is transferred through these contact forces. The effective stress is therefore the average stress carried by the soil grains. The second component is the pore water pressure, which arises from the water trapped inside the soil pores. It is present if the soil is located below the groundwater table, whereas the soil will be fully saturated and submerged. The pore water pressure will act as buoyancy on the soil particles and reduce the effective stress. This is due to an upwards force exerted by the water on the soil grains, which opposes the weight of the soil. The total stress formula presented previously accounted for the weight of both soil and water. The total stress formula can also be formulated based on the effective stress and pore water pressure components. This makes it possible to distinguish between the magnitude of the effective stress and the pore water pressure. Let's consider soil above the groundwater table. The total stress is defined based on the effective stress and the pore water pressure. Since the soil is above the water table, no buoyancy is present and the pore water pressure is equal to zero. The total stress is therefore equal to the effective stress, which can be stated as the unit weight of the soil multiplied by the height of the soil layer, as shown previously. If we consider a plane through the soil grains, the average normal stress on the soil grains can be visualized. Let's now consider the same soil, but below the groundwater table. The total stress is again defined in terms of effective stress and pore water pressure. However, this time the pore water pressure is equal to the unit weight of the water multiplied by the height of the water table. This is sometimes referred to as the hydrostatic pressure distribution of water. The formula for effective stress can be derived by isolating the effective stress in the total stress formula and including the general total stress definition shown previously. This formulation of effective stress is based on the effective or buoyant unit weight of the soil, which is the unit weight of the soil with the buoyancy from the water subtracted. This formula is commonly used to determine the effective stress below the groundwater table, since this formula can be used without knowing the total stress or the pore water pressure. If we consider a plane through the soil grains again, the average normal stress is composed of both the effective stress and the pore water pressure, unlike the soil considered above the groundwater table. Let's take a look at a few examples. In the first scenario, we consider a soil where the groundwater table is located below the considered volume. Based on this information, we can set the pore water pressure equal to 0. Since the water is located below the considered volume, no buoyancy should be taken into account. The effective stress is therefore solely based on the soil's unit weight. The total stress is equal to the effective stress. The groundwater table now rises. This means that the pore water pressure will be present in the soil volume's lower part. The presence of the water reduces the effective stress. However, the effective stress is not changed above the groundwater table. Therefore, changes in the water table are crucial, since a reduction in effective stress can increase the risk of failure in some instances. The magnitude of the total stress did not change when the water table rose, since the weight of soil and water is considered the same. If the soil volume now consists of two soil deposits, only the effective stress and total stress is changed. The pore water pressure is the same, since the groundwater table stays the same. The effective stress in the upper part of the soil volume is still based on the unit weight without buoyancy. In the lower part, the effective stress is based on the unit weight with buoyancy, thus the effective unit weight. Compared to the other examples, the total stress increases for the second layer, since the unit weight is assumed higher. But what if the groundwater table exceeds the terrain level? Since the pore water pressure starts at the water table, it exceeds 0 at the top of the soil volume. The effective stress for both soil deposits is based on the effective unit weight, since both deposits are affected by buoyancy from the water. The total stress is determined as the sum of the effective stress and the pore water pressure. One of the stress formulas is no longer valid. Understanding the relationship between total stress, effective stress, and pore water pressure is crucial for making accurate and safe engineering decisions in various construction projects. This concludes the video. The table presented shows the variables used in the video and their general units. To support the channel, please like and subscribe.